in the country.
Yeah, it's working now. I will just share this thing, then we can start. Okay. Record. Cloud. Yeah, Bevela ma'am, you can start now.
Yeah. Post disabled participant screen sharing. George sir?
Yes, done. You can start now.
Yeah. Good evening, participants. The next speaker of our session is Dr. Goma M. Ali. The topic of his talk will be nanomaterials for energy storage applications. And it's my honor to introduce Dr. Goma, who's an assistant professor at the Department of Chemistry, Faculty of Science, Al-Azhar University, Egypt. He has 12 years of experience working in research area of material science, nanocomposites, humidity sensing, graphene, supercapacitors, water treatment, and drug delivery. He's the recipient of some national and international prizes and awards. Dr. Goma has published over 82 journal articles as well as 5 book chapters on a broad range of cross-disciplinary research fields, including advanced multifunctional materials, nanotechnology, supercapacitor, water treatment, humidity sensing, biosensing, and corrosion, drug delivery, and materials for energy applications. Dr. Goma has served as both a senior editor and editorial board member of many international journals. Dr. Goma, you can start your lecture.
Thank you so much, Dr. Maria, for your nice introduction, and thanks for all your organizing team. And it's my pleasure to be a part of your great conference. So, without further delay, let me start to sharing my screen and start my presentation. So, my presentation seen by you now. Hello?
Yeah, you can carry on.
Yeah.
Okay. Good evening to all participants, and it's my pleasure to be with you today. And I'm going to share some of my research interest. My talk today will be titled Recycled Nanomaterials for Energy Storage Supercapacitors Applications. Okay, like our previous talk was on battery. So my talk will be continuous or the same line on that with the previous talk presentation. So some of us maybe know what is the supercapacitor. Supercapacitors are defined as alternative energy storage devices that simply devices that can store electrical energy. It has higher power density than batteries, and it has fast charge and discharge time, and it has long lifetime. As we can see here in this diagram, which is a popular diagram called dragon plot. So this plot showing the most of the energy storage devices based on the relation between their power density and power energy. So supercapacitors here in this triangle shows that has high power density compared to batteries. So supercapacitors can be applied for many different applications, including electrical vehicles, household electronics, emerging doors in airplane, and in PC power supply. So a lot of application of our daily life could use supercapacitors. So based on the mechanism of storing the energy or the electrical charge of this supercapacitor. Supercapacitor could be classified into two main categories: electro double layer capacitors and pseudo capacitors or pseudo capacitors. For the electro double layer capacitors, the device stores the electrical charge or the electrical energy based on formation of double layer on the surface of the electrode material. So in this case, no Faradic reaction takes place or no charge transfer. So, and the electrical charge are just accumulated as a multi-layers or double layers of the ions or the charge on the surface of the electrode materials. On the other side, on the other hand, the pseudo capacitance stores the electrical energy or charge based
Dr.
on
Thoma?
Faradic. Yes.
Sorry to interrupt. Your audio is not good. Can you check? Can you use your headphones or headset?
Okay, I will try to use my.
There is some disturbance.
Now it's okay. Now I'm using the headphone. So is it okay now? Clear?
It's still there.
Till then. So what I should do?
Yeah, you continue. You carry on.
Okay. So continue. So supercapacitor could be classified into two main categories: electro double layer capacitance and pseudo capacitance. The pseudo capacitance stores the electrical energy in terms of Faradic reaction or redox reaction happens on the surface of the electrode materials. Okay, what are the materials could be used for supercapacitors electrode, or what is the materials could be candidate for supercapacitors application? For electro double layer capacitors, most of the carbon material are the best candidates for this application, including activated carbon, C60, graphene, or reduced graphene oxide, carbon nanosphere, and carbon nanotube. For the pseudo capacitance, which include electrical reaction or electrochemical reaction, those include metal oxide such as manganese dioxide, cobalt oxide, and ruthenium oxide, or conducting polymer like polyaniline, polypyrrole, and polythiophene. So this diagram shows the supercapacitors in both charge and discharge case. In a charge case, the ions are accumulated on the surface of the electrode materials, and in this charge case, the ions are distributed among the electrolytes. So most candidates or most popular candidates for supercapacitors electrode materials are manganese oxide and carbon materials. So why manganese oxide? Because it has a lot of advantages which recommend it to be a suitable candidate for supercapacitors electrode material or supercapacitor application, which is major manganese oxide, environmentally friendly, abundance, low cost, has different crystallographic structures, various morphology, including nanoflower, nanorod, as we can see from the scanning electron microscope image later on. And it has high theoretical capacitance, which is around 1,370 farad per gram, and broad potential window. It could work under wide potential range of the applied voltage. On the other hand, carbon materials are long lifetime, high conductivity, abundance, and ability to trap charge, and high surface area and more porous structures. So these are the main or the most popular candidates for supercapacitors applications. We can use this material to prepare or to evaluate the supercapacitors. But this preparing of these materials from chemical source is the most challenge, or because it's highly cost. Therefore, in my research, I try to find alternative source to prepare a materials for supercapacitor application with low cost. Thus, we rely on recycling. So, waste sources, we have a lot of sources as a waste, like zinc carbon battery, spent carbon battery, which has high manganese content, and lithium ion battery, spent lithium ion battery, which has high cobalt content, and we have agriculture waste, which has high carbon content. So from these waste materials, we can recycle the component to be a good material for the supercapacitor application. So from these waste materials, from example, from spent zinc carbon battery, we can recycle manganese oxide to be used as supercapacitor material, and from lithium ion battery, which has high content of cobalt, we can recycle cobalt oxide and use it as supercapacitor electrode material. And from different agriculture waste, we can recycle carbon in different form, porous carbon nanostructure, carbon nanospheres, and we use it as supercapacitors application. So we start from spent carbon battery. For example, manganese oxide from spent battery. We start from zinc carbon batteries, our dry battery. By using electrochemical technique, electrodeposition technique, after dismantle to their most component part. So we use zinc cathode powder, which is cobalt, which is manganese oxide and carbon material. We leaching this carbon, which is a cathode battery, to get a solution of manganese species. After we get the solution of manganese species, we electrodeposited the manganese by applying electrical to produce manganese dioxide nanoflower sheets. And this is a PSM image of the manganese oxide under PSM, showing the nanoflower morphology of the manganese oxide. This nanoflower morphology, actually, it's interesting because it allows the ions, or electrolyte ions, to penetrate among this porous structure. So this is the X-ray diffraction for the recovered manganese oxide from zinc carbon battery. And we tested this manganese oxide as supercapacitor electrode. So we ran cyclic voltammetry, scan cyclic voltammetry, and shows the rectangular shape of cyclic voltammetry, and also charge time. And based on some calculation from these curves, manganese oxide nanoflower morphology recycled from zinc carbon battery shows high capacitance value of around 210 farad per gram at current density around 4.1 ampere per gram, and almost high capacitance at various different current density applied. And this work was published in Material Research Bulletin. And same source, zinc carbon battery, we recycling manganese oxide by different technique or different method, which is using cyclic voltammetry by applying different voltage, by applying voltage for many cycles, and we successfully convert the cathode powder of the battery into nanoflower structure of manganese oxide. And this is the mechanism of during the charging and discharging cycles. And successfully, we got the nanoflower morphology of manganese oxide compared to just clusters of aggregated particles of manganese of the cathode powder. So this is the cathode powder before conversion, and this is the manganese oxide nanoflower morphology after applying cyclic voltammetry to obtain manganese oxide material. So same manganese oxide recovered from this zinc carbon battery was tested for supercapacitors application and showing the rectangular shape of, in the CV curves. And here we compared with the cathode material before conversion. For example, the dot lines, the dot curves for the cyclic voltammetry for the cathode powder. And after conversion into nanoflower, manganese oxide shows high rectangular shape and high current density, indicating more charge accumulated or stored in the manganese oxide nanoflower shape. Same for charge-discharge. It has been tested for a different current density and showing linear charging and discharging curves at different current density. And for specific capacitance calculations, it shows higher or high specific capacitance of around 300 farad per gram for at current density of around 0.1 ampere per gram, compared which is around 6 times higher than the dry cathode powder. So by converting the cathode powder of the spent carbon battery into nanoflower morphology, we can apply this product in supercapacitor application, and we got more than 6 times higher specific capacitance application. So this work also published in Ceramic International 2017. One more example, we use the spent battery cathode powder, and at this time we combine with graphene. I mean, we synthesize not purely manganese oxide as previous two examples. In this case, we add graphene oxide, and simultaneously, the graphene oxide has been reduced by applying cyclic voltammetry and converted into reduced graphene oxide, and successfully we obtained the nanocomposite structure of manganese oxide species distributed on the surface of graphene sheets. As we can see here in the TM image, this is graphene, pure graphene, showing the graphene nanosheets, and this is pure manganese oxide, showing the aggregated particle of manganese oxide, and for the composite showing the manganese oxide particles or nanoparticles distributed on the graphene sheets. In this case, we want to study the synergetic effect of these composites as supercapacitors electrode. So here's a Raman spectrum for pure manganese oxide and pure graphene, and the composite showing the peaks for or the bands for both materials, indicating the successfully combination of the two materials for this composite. And as usual, we tested this material or this nanocomposite for supercapacitor application, and it shows cyclic voltammetry, rectangular cyclic voltammetry, and linear charge curves. And we tested for different applied current density. And here, the synergetic effect of the combination between pseudo and electrodouble layer materials, showing increment of the specific capacitance of around 500 farad per gram. So the combination between graphene as a carbon double layer materials with manganese oxide increased the capacitance of manganese oxide by around 2 times higher. Also, this work published in Ceramic International 2018. So in these 3 examples, we successfully prepared manganese oxide from waste source from spent zinc carbon battery. So alternatively, or on the other hand, we try to compare with the chemically produced manganese oxide. So we use the same technique we applied for electrodeposition technique, and to deposited manganese oxide from chemical source from potassium permanganate. And we applied 2 techniques. One is applying fixed current, and one applied fixed potential. And in both techniques, we successfully obtained manganese oxide with nanoflower morphology. But in one technique, the thickness of the sheets are more thinner than the other one. And the this material also prepared from chemical source using electrodeposition techniques shows excellent electrochemical behavior and high stability up to 5,000 cycles of using charging the supercapacitors applied. Thus, we can confirm from up to now, we can confirm that the material manganese oxide, which recycled from zinc carbon battery, is a perfect or excellent candidate for supercapacitor application, and it shows the same behavior or more, maybe more excellent behavior than the chemically produced manganese dioxide. This work published in Current Applied Science. Another example for also recycling material for supercapacitors applications, which is recycling cobalt oxide from lithium ion battery, from spent lithium ion battery. After we use this lithium ion battery, we use for many kinds of electronics device in our daily life, like our phone, our laptop, and everything. So we use the spent batteries to recycle the cobalt oxide from this spent battery. So successfully, cobalt oxide has been recycled from spent lithium-ion battery using not electrodeposition techniques, but using magnetic electrodeposition. So combination of applying electrical power with magnetic power. Our aim for this, for using magnetic power, is to make alignment for the cobalt species. As we know, the cobalt oxide has magnetic properties. So using electrodeposition technique, it could be precipitated or could be obtained, but maybe in random manner. So using or applying additive magnetic power, it could be could make the cobalt species precipitated on the substrate using excellent or good manner. And we successfully got this one, as the cobalt species successfully precipitated using in the form of nanosheet structure, and compared to the without applying magnetic power, it's just randomly precipitated as spheres. So the electrochemical testings of the recycled cobalt species, cobalt oxide species, showing the pseudo-capacitance behavior of cobalt oxide, as cobalt oxide could be oxidized and reduced, so it behave as pseudo-capacitance materials, and a different scan rate shows the increment of current density. And interestingly, it shows high stability. It means it could be used for 5,000 cycle, mean charging and discharging, and we can consider this is a full use of the device or the supercapacitors. And after 5,000 times, it could still maintains high stable, more than higher than around 90% of its original capacitance. On the other hand, carbon material, which behave as double layer capacitance, it could be successfully obtained from agriculture waste. We have so many kinds of agriculture waste in our life, and thus we can obtain carbon materials from this agriculture waste. So we start with oil palm leaves, which are most abundant in Asia countries like Malaysia, Indonesia, and sometimes India. So this palm oil leaves is most abundant. So we use this palm oil leaves, grinding, then pyrolysis at 600 or around 600 degrees in nitrogen flow. So we obtained porous carbon nanosphere, and this is some characterization showing the carbon structure of the paired materials, Raman and X-ray fractions. And under PSM and TEM investigation showing the spherical particles of carbon nanomaterials. So this material has been tested for electrochemical application, testing for supercapacitor application. It's showing almost rectangular like CV voltammogram, and also almost linear charge and discharge time, and showing capacitance of around 250 farad per gram at current density around 0.2 ampere per gram, and the capacitance decrease up to 150 at 1 ampere per gram. And this is the Nyquist plot or impedance spectra showing very or high conducting material, which shows a resistance of around 0.0 ohm, which we call it solution resistance, and charge transfer resistance around 1 ohm, indicating this very conducting materials. And stability also, we have tested this one, this material up to 1000 cycle. So it shows around more than 95% of its original capacitance value, even after 1000 cycle of using this device. Also, this material has been tested for wider potential range up to 2 volt, and also it shows electrochemical stability or behavior under this wide range up to 2 volt using cyclic voltammetry at different voltage range, and even using the charge up to 2 volt, and it shows around 190 farad per gram specific capacitance and power density of around 20 watt-hour per kg. And also stability for 1000 cycles, showing more than 90% of the capacitance retention is still there. Another example for carbon material prepared from agriculture waste is porous carbon nanosphere prepared from lab precursors. So from this precursor agriculture source, we successfully obtained carbon nanomaterials at different calcination temperature, or different pyrolysis temperatures, 500, 700, 800, and most of them showing the spherical particles of the spherical particles of the carbon material, and here the particle size distribution showing the nano range size of this material. And the material has been used as supercapacitor electrode, and the supercapacitors are investigated under different potential range up to 1.6 volt, and it shows the rectangular shape or rectangular voltammogram indicating the electrodouble layer behavior of these materials, and showing linear charge curve at different potential window and different current density, and it shows capacitance around 130 farad per gram and energy density around 18 watt-hour per kg. Also, we can conclude here from this one is excellent candidate for supercapacitors application, and it will be used as supercapacitor electrode material. Also, we have prepared porous carbon nanosphere from another waste source, which is alum sipapil, and we successfully got the spherical particles of carbon materials, and same investigated for supercapacitors applications at different potential window, and it shows around, maybe here this time is low specific capacitance around 80, maybe this one is not pure carbon materials obtained, so it shows around 80 farad per gram and 22 watt-hour per kg energy density, and this one is from published material in Biomass Converger journal. Also from porous carbon nanomaterials could be prepared from Sago Park waste precursor, and it could be prepared as carbon nanospheres, spherical carbon nanoparticles, and shows some interesting electrochemical properties which allow them or recommend them to be suitable candidates for supercapacitors application. This work published in Essays on Sustainable Chemistry in engineering. And I think last examples, we carbon, activated carbon, it could be prepared from bulk crinkle shell, and it has been impregnated with calcium oxide from eggshell. So here we use two different waste precursor, which is bulk crinkle shells to obtain activated carbon, and eggshells to obtain calcium oxide to prepare a composite of this calcium oxide activated carbon. And here we obtain the honeycomb structure of carbon materials, very porous structure of the activated carbon materials, and the cobalt oxide species are distributed on the surface of this carbon material. And this spherical, this porous carbon structures is interesting for the electrochemical application or supercapacitor application, since it allows the ions accumulate or penetrate among this porous structure. And here is some of the electrochemical testing of the this composites or this nanocomposites, showing charge discharge time with very low. Here we can, this one is, we call it IR drop in the supercapacitor application. So this material shows very low IR drop, around less than 0.7%. This IR drop indicates the material, is it conducting or resistance? The material which has high resistance, it shows high IR drop. But the material which is more conducting shows very low IR drop. So this material indicates the high conductivity of the combination of calcium oxide with activated carbon materials, and showing around less than 0.7 IR drop. And it shows around 230 farad per gram specific capacitance, compared with around 80 or 70 farad per gram for pure activated carbon without calcium oxide impregnation. So here we compare the nanocomposite of calcium oxide with activated carbon from bulk crinkle shell with pure activated carbon from bulk crinkle shell. So here the charge showing wider curve or long time curve, showing the higher charge accumulated, and also the specific capacitance calculation showing the specific capacitance for the nanocomposites is more than 2 times or maybe 3 times higher than pure activated carbon from the same source. I don't know how many minutes left for me, so would I go to conclusion? So to sum up, so manganese oxide could be obtained from waste resource or waste precursor like zinc carbon battery, using different application, different methods, including electrode deposition or cyclic voltammetry conversion, and it could be obtained in a pure form, in NO2 nanoflower form, or we can impregnate with graphene oxide or any carbon material. So this manganese oxide obtained from this waste source could be applied for the supercapacitors application, and it shows high specific capacitance value and interesting behavior or excellent behavior of electrochemical testings, and it shows high stability, which recommended to be used as supercapacitors electrode materials. On the other hand, carbon materials, it could be prepared from different varieties of waste precursors like different agricultural waste, and it could be obtained in terms of porous nanocarbon or carbon nanospheres, and it could be applied for supercapacitors application. And here is just photos of some exhibitions using our prepared materials and some awards. Some of my collaborators among some universities in USA, Singapore, Australia, and so on. And some photos from our lab actually in Malaysia. This one during my PhD and after PhD. And thank you.
Thank you, Dr. Verma. I have a few questions raised by the audience. Is there any non-carbon material which can act as EDLC?
Excuse me?
Is there any non-carbon material which can act as EDLC?
If I hear you correctly, the carbon material, all carbon materials behave as EDLC, electro double layer capacitors. Yes.
Okay. So they were asking about non-carbon material.
Non-carbon material?
Which can act as EDLC.
Yeah, manganese oxide, it could act as ELD, electro double layer capacitance. It shows the cyclic voltammeter as double layer capacitance, but actually it is pseudo capacitance. The story is complicated. What we can summarize is manganese oxide has multi oxidation state, different oxidation state. So it undergoes successful or continuous redox reaction. So the redox peaks cannot be identified in the CV voltammogram. So I mean we consider it as 3 redox peaks are communicated or interacted among each other. So the final output of the CV of MnO2 is similar to electro double layer capacitor, but in fact it is pseudo capacitance materials as metal oxide.
Okay, thank you. Next, how to extract MnO2 from waste materials? How to extract MnO2 from waste materials?
Yes, from waste materials. Firstly, the waste material which has high content of manganese oxide is zinc carbon battery. So from zinc carbon battery, we just simply dismantle the zinc carbon battery into stainless steel and plastic parts. Then we use the cathode powder. Cathode powder it's component of carbon and manganese oxide. Actually, manganese Mn3O4, different oxidation state Mn3O4, which is not interesting in supercapacitor application. The target one for supercapacitor application is MnO2. So from this powder, we do leaching to dissolve this materials. Then we apply electrode deposition technique to obtain MnO2 nanoflower morphology. Either we apply electrode deposition technique or we apply cyclic voltammetry, same electrochemical technique. So most probably by electrochemical deposition of the cathode material of zinc carbon spent battery, we can obtain the manganese oxide nanoflower morphology.
Thank you, Dr. Goma, for accepting our invitation.
Thank you.
Yeah, thank you, Dr. Goma, for joining. Yeah, thank you so much. Thank you.
Really, I thank you for this kind invitation and to be a part of your great conference. Hope we see us again.
Sure, definitely. It would be a pleasure. Thank you. Have a good day. Yeah, bye.
Madam.
Yeah. How are you?
I'm fine. How are you?
Yeah, we are fine. So this is our team. We were working for the conference.
Okay, nice to meet you all.
Yeah. So thank you once again for accepting our invitation. I think last time you were unable to make it up to our ICNAN.
Yeah. It's my pleasure.
Yeah, our pleasure too. So for your session, Dr. Satya Narayanan, who is here with us, he'll be chairing the session, and he will introduce you first. And then after his introduction, you can start sharing your screen, put it on a presentation mode, and then it will be in YouTube, live streamed.
Okay.
The participants have already joined the session.
Okay, thank you so much.
Yeah. So George, can we get started?
Yes, yes.
Yes, okay. So over to Dr. Satya Narayanan.
I will share the screen.
Yeah.
Is my screen visible, ma'am?
No, Satya, we
Is it visible now, ma'am?
no, Dr. Satya.
Not yet.
Okay.
Satya, let me share this PPT. Yeah. You can go ahead.
Okay. Okay. Very VCAN 2020. We welcome you for this next session titled Nanostructured Materials, Potential Applications to Energy and Environment. And it's I'm really honored and privileged to introduce the speaker of this session, Dr. Mangala Raja. He's a full professor in the Department of Materials Engineering from University of Concepcion at Chile. His research interests in the areas of nanotechnology driven advanced ceramics, which is functional ceramics for energy and environmental applications, and micro nanostructure property relationship of functional and structural ceramics and metallic composite materials. He has authored more than 190 international publications, and he has authored 12 book chapters, and he has filed 3 patents, and he is the editor of a book, and he has more than 150 research presentations in several international conferences. Also been the investigator and co-investigator of 35 research projects funded by ANID, National Agency for Research Development, Government of Chile. So with this short intro, I kindly request Dr. Ramalinga Vishwanathan to deliver the talk. Thank you.
Thank you, Dr. Satya Narayanan. It's my pleasure. And firstly, I would like to thank Professor Nirmala for this opportunity. Well, I can share my presentation here. I hope you can see my presentation. Is it?
Yeah, we are able to see.
Yeah, okay. Well, just today, I would like to talk about something that what we are doing at University of Concepcion, that Chile, the other part of the world. I think very less people, Indian people are working here. And we have some different kind of environment here. So just I want to give a overview about the work that what we are doing here towards the application to potential application to energy and the environment, especially in our laboratory, that advanced ceramics and nanotechnology laboratory that we have established here. Well, I'm showing this picture, the global horizontal irradiation. Maybe I will come just.
Sorry to interrupt you. Your slide is not visible. Can you make it in presentation mode?
Presentation. Is it already in presentation?
Because it looks blank.
Okay. Now?
Yeah, now it works.
Okay. Okay. Just I'm showing this slide because that I would like to show that where we are, that the other end of the world, and that also showing the EV index of all around the world, the map showing. maybe the why I'm showing this map, maybe I will come to that later. Before that, I will give content of my talk that I would like to give an introduction about the trends what currently on nanomaterials, especially in our side, and also the importance of miniaturization and also the research lines from science to applications, result, particularly environment, energy, and conclusion of the talk. Well, we know that long many years we are working on nanostructured materials. The current trend is everyone knows that it is mainly focused on energy and environment. Particularly, we are working on the solid oxide fuel cells, solar cells, optoelectronic devices, and magnetic refrigeration on the energy side. On the environment side, that we are working on sunscreen cream, photocatalysis, and freestanding some films for wastewater treatments and filtration. And especially when we talk about the nanomaterials, I can take in two ways, like the particles in form of particles, as well as in form of bulk materials. So I just want to take two examples on both sides, energy and environment. And in energy side, I just want to take the bulk nanostructured materials, and environment section, I just want to take nanoparticles, that how it impact for sunscreen cream applications. Both projects are currently we are working intensely. We are working for developing application directly to the applications, not from the starting material, from the precursor materials to fabrication, and finally towards the performance of the materials. In that case of solid oxide fuel cells, we are working on the development of prototype solid oxide fuel cells supported on mini-tubular nickel gadolinium doped ceria anodes as an industrially viable energy source. Like it's kind of making solid oxide fuel cells, stacked cells, and not a single cell, stacked cell, to increase the energy efficiency, so that we can use for certain applications. Of course, it depends how much energy we are generating. So in that focus, we are working on the fabrication of solid oxide fuel cells and the stacks to obtain a certain level of energy. Well, I just want everyone knows that a fuel cell is a device that transforms chemical energy of fuel directly into electrical energy. Solid oxide fuel cell, which contains mainly three components: ceramic electrodes, two electrodes like anodes and cathode, and one ceramic electrolyte, which is more important. And this kind of solid oxide fuel cells normally we know that it operates at high temperature, around 600 to 1000 degrees, and also it has a high efficiency. But the critical things are we have to understand the mechanism of how it works, that how we can improve, how we can minimize the device structure, and how we can improve the efficiency. It's more important. So then on that concern that we are working on the anode electric and ionic conductors, anode and cathode, and my microporous structure developed anodes and cathode. In electrolyte sites, we are working on the ionic conducting materials with more high dense. That in all cases, we consider that we have to make it in nanostructures, nanograins, in the form of developing nanograins. And that I previously explained that normally this solid oxide fuel cells works on high temperature, but our intention is to decrease the working temperature, at the same time increase the efficiency. So we have to focus the new materials. The current, so it depends how much this slide source, how much energy that generating, which different kind of devices that we can use. So the strategy is to improve the performance of the solid fuel cells, cell support, geometry, and electrolyte materials. So these three is more important because cell support, what kind of, whether it is anode support or electrolyte support, it's important. We have to design. And geometry case, there are different structured like tubular and planar and zigzag sized geometries are available in the market, but which is more convenient and which is more usable. Not only that we are focusing on the electronic side, but as well as the mechanical side point of view also, we got to see the strength. How can we have a good strength of materials, not only focusing on the conductivity, also the mechanical properties. Then the final part is the electrolyte material. So what is the need of importance of electrolyte material? Normally, traditionally, that people, that use electrolyte support material, support fuel cells with a sandwich like anode and cathode. In this case, the ohmic polarization is predominant in solid oxide fuel cells. So it is produced in the electrolyte. So to reduce the electrolyte thickness reduces the polarization. So we have to reduce the thin walled electrolyte. So that's our aim to focus. Also to make it find out new materials and developing new material so that in that nanostructure we can reduce the operating temperature. So we decided to fabricate anode supported cell. So traditionally, people in the world, around the world, even the companies in the research centers, most work have done in Etria stabilized zirconia, which I mentioned. Normally it works on the high temperature, and the current trend is we are developing the gadolinium doped ceria materials, electrolyte materials, which can decrease the operating temperature. And it also has a wide field of application and decreasing the start times and reducing the material costs. That because obviously when we reduce the operating temperature, the other causes can influence, So in the general objective is to manufacture mini tubular nickel, that is from nickel oxide. We derive nickel, that we are reducing the nickel oxide to nickel, and nickel GDC based anodic support fuel cells. That is. I'm sorry that some letters are in Spanish. Maybe it is because our way of a language here in Spanish. So this slide shows the production of mini tubes that from the tube that we are applying the coating of electrolyte. Over that electrolyte, we are coating the cathode coating. Then finally, we are going to sinter the materials. That sinter also we do at different stages. For example, after fabricating the anode tubes, that we have to sinter around some 1,200 to 1,400. Then together electrolyte coating and cathode coating, we sintered again this material. This not material. I mean, I can say that that's cells. Again, the secondary synthesis. Normally, these powders, everyone knows that these powders we do on the normal synthesis. We adopt a salt gel or combustion synthesis. And in this case, I just showed the combustion synthesis. Everyone knows that how can do the combustion synthesis. It's very simple, that mixing the metallic nitrates and making it combust at a furnace which I already kept at 500 degrees centigrade. Then we easily get the formulaic success. The structures we can gently grind and we can easily get the nano materials. But getting nanomaterial, preparing nanomaterial is not a big deal. But at the same time, it's more important that size and shape is more important. So we, in this case, we, even though it's combustion synthesis, we can control the shape, not only size, we can control the shape. And after this, obtaining these powders, more important that obtaining the paste of the precursor, that paste which we will use for fabricating their ceramic tubes. So what here you can find the composition, that what are the materials, polymers included in the paste, which can act as a binder. Also, this can be easily extrudable, and that's more important, because everyone can prepare the paste, but fabrication without defects is more important, because when we have defects, like cracks and other defects, if we present, the mechanically it will not be stable. So it's more important to have the free cracks tubes, because we are going to sinter the tubes, at the same time, our aim to focus the porous tube. So it needs to have porous, at the same time without cracks, and fine shaped tubes. So the paste made a big role in this fabricating the ceramic anodes, which will be used for ceramic fuel cells. So this paste we have formulated. This is a patent work that we have filed, and recently we also have filed for US patent, which is the specialty of the paste is, that normally the paste sometimes after 1 or 2 days, it will lose the characteristics, like the humidity and the other plasticity, viscosity characteristics of all characteristics. But in our paste that we have obtained the patent here in Chile, and also we have applied the US patent, that till 3 months it's not losing any properties. Without losing any property, it retains its original properties till 3 months. So that is the specialty of the paste. That you can find how much liquid phase and solid phase in the paste that we are. For this making the paste, we mix the polymers that I mentioned in the composition in the previous slides, and makes a mixture. And from making from this paste that we extrude. Of course, we have there are 2 types of extrusions: automatic extrusion, because also they are manually extruded. In the automatic extrusion, that we have to have, big amount of paste, so that in this case we need a very little amount of materials, that because we are developing mini tubes, and we can say that in our mini tubes, we can sometimes say that it's micro tubes, because that the diameter and the thickness of the tubes may be in the range of microns, and in the range of microns, so the grains are in the nano level. So this will give the advantage for fabricating tubes. When we size direction, obviously we can stack more cells in 1 centimeter cube. That's what our aim. That many, for example, some 9 cells in 1 centimeter cubics, that is kind of integration of cells. So we fabricate this material by extrusion process. And of course, we also do the characteristic of this paste by using different equipments like viscoriometers, like that to identify to maintain the viscosity and other properties, plasticity of the materials. This slide shows the reduction of sintered nickel oxide, GDC Carolina doped seria, microtubular anodes, that where how it is looks the pore structures overall. You can see the green color changes of tubes after reduction, like green, sintered, and reduced tubes. Green in the sense I can say so that it is as fabricated, a green body of the materials. So it is uniformly porous tubes with high mechanical strength, appreciable mechanical strength. The same way, not for fabrication of the tube, the same way for precursor synthesis of electrolyte and cathode powders, also we adopt the combustion method, also sol-gel method, but I have shown here only. In some cases we use precipitation methods also, but in this case I have shown only the combustion method, which is very easy to make a rapid synthesis. So we also developing this kind of process not in the laboratory scale. Since you can understand that since Chile is a small country, normally the government is focusing in the industrially oriented projects. So we not only we do the focus of our aim of all research in the laboratory scale, we also make it in the industrial scale. So this electrolyte powder also we synthesize ourselves, and we make homemade coatings, like because it's kind of new invention. We can use traditional and available techniques like, but every time when new technology is recurring, and that we have to identify new techniques of fabrication, new techniques of different kinds in different stages. Like, so in that case, we also find out the laboratory scale, made brush painting of this material, that using the kind of spray coating that we coated on the over the anode tips, that what we fabricated. That tubes you can see here on the white colors, and this after coating this, we coat the sinter this material at different temperature. We can sinter this material, for example, 1200, to obtain a high dense material over the uniformly porous anode. That is more important. That is, we have to obtain a highly thin, at the same time highly thin and highly dense material, that you can see here the structure of how it is look like. With several trial, we obtained that highly densely arranged green grains on the electrolyte layer. And in the same way, also we worked on the cathode powder to coat over the electrolyte. So it's three stages. Finally, you can see that fabricated tubes, how it's look like about 5 centimeter long, but the thickness but the diameter is in the 1 mm thickness, like 1 mm thickness. You can find. I will show you in the next slides. This also after we got to sintered again. So final cell, we are getting that porous anode and high density electrolyte coating with minimum thickness, and also again porous cathode with minimum thickness. Is look like the cross section I have shown here. Like you can see the thickness of the anode. It's around 1 mm. You can see some cases you can see, so from 800 micrometer to 900 micrometers, so maximum. So in that case, you can imagine that how much thickness of so the total diameter is like 4 mm, and that is showing in the left side slides. So it's a complete cross section of the cell, the fabricated cell. So that after that we test the cells. In this case, for example, I told you in the beginning that our aim is to decrease the operating temperature to increase the efficiency. So approximately 0.6 watt per centimeter cube that we generated, say 600. Before that, the pandemic situation, that we worked on developing. Then go to nearly 1 watt per centimeter cube that we develop that stock that say each cell that we stacked in different modes that I will explain. For example, designing stack cell fabrication designing is also more important, that as I mentioned previously, because each cell can provide, for example, I can say that 1 watt per centimeter cubic, but when we stack the cell, we cannot expect that, for example, here I can show that 4 cells. So 4 watt per centimeter cube, I cannot. But in the same time, when we only integrate, stack the cells, maybe it gives some 3 watt or something below 4 something. But when you use some converter, it's more it's easily that we can improve the efficiency, so that we are working. That's why we are working on the team of like different field people, like materials, chemicals, and electrical people. So with a group of people, that it's a more important, sir. Everyone knows that mechanism. So how can in our part that we can develop with the materials, but the conversion of energy, normally the people in the electrical and electronics department, they know very well than materials people. But so our team is equipped with different experts in different departments. So normally mainly the research students, and they are working on this kind of developing stacked cells. Here you can see the other kind of stacking, like in parallel mode. Here you can see it in series mode and parallel mode. This kind is showing the stack cell testing. So as I mentioned that we also developed a new kind of stacking design that I previously explained in the slides, that new design with some design of alloy made materials, that we stacked cell individual cells with separately, not only by touching each other. So in different way that we are working on cell. In this kind that we use the converters, which can easily increase the efficiency by help of that. For example, if we stack of 9 cells in 1 centimeter cubic, maybe as I mentioned, in 9 cells maybe produce 9 watt per centimeter cubic, but in our case it produces more than 15 because of using the converters. So it is more important that if you are using the converter, but in the same thing that what we are doing in the case of solar cells also, that when you use the converters, you can easily integrate and increase the efficiency of the cells. So our aim is to focus for the some drone applications, and that because for local application, because of the need of the government, and that especially in drone, which can at least work for at least an hour in this technology. At the same time, solid oxide fuel cells, the current trend is also changing towards the reversible solid oxide fuel cells, which is can operate at in both modes, like SOFC mode and SOEC mode. It means a solid oxide electrolyte cell, electrolyte cell mode. Because in Chile, you have a lot of solar energy source, like we have the north part of Chile is full of desert. So the SOFC mode can operate at nighttime, and SOFC mode can operate in the daytime, like different modes of trend is operating. So we have now also started the same thing what we are doing in SOFC. We also started in reversible solid oxide fuel cell developing materials and fabricating the material. It's so easy because that we have already experienced in the solid oxide fuel cell. So it's just to operate in the different mode. In that case, we can also generate the hydrogen as an, because now recently hydrogen, that helping for many energy utilizing for energy applications. So the conclusion of the in the current project is, of course, we already finished major part. So it was possible to manufacture SOFC, a mini tubular fuel cell supported on an anode type nickel oxide, a GDC based material, which can generate power between 0.3, and of course we reach in the last attempt we reach nearly 0.1 watt per centimeter cube at 600. So we have already also made the stacking. So the aim is to focus at least 100 watt with medium power mobile applications, and that is in under process. Hopefully, maybe in the next year we can achieve this goal. We believe that. And it's in the second talk, second case that I would like to explain that as a particle, how it can influence the nanostructure material, influence different applications. I can say that in the last topic that I mentioned, the bulk material, but as a form of particle, how can it influence? For example, I mentioned that in the first slide that the overall map of the solar energy diagram in the around the world, that UV index, how it affects in the world. You can find that the north of Chile, the UV index is very high. So based on the needs of local needs, we also developed a prototype sunscreen cream based on coastal nanostructures of zinc oxide and cerium oxide, and cerium oxide, zinc oxide, both in vice versa, for coastal structure for skincare applications. And we developed a cream. This project also that we work with pharmaceutical department and material department, because of the testing that we have sent the samples to the Brazil for to in vivo applications. That recently in the skin cancer is increasing. Almost it coming the third place in the most common cancer, and we also know that the most of the skin cream is not a productive one. It can give some side effect. Even myself, I also experienced this kind of cream, that when we visit different countries, when we go for sunbath or sunlight exposure, it can react with our skins. So by considering this kind of factors, we also developed a cream based on this material to protect the skin. So in this case, we synthesize nanoparticles of separate zinc oxide and cerium oxide, as well as core cell transistor together in zinc oxide and cerium oxide core cell, and formulating this material with normal cream that is fabricated, produced in the pharmaceutical department, that we applied, and we tested the SPF factor, that sunscreen factor, that it gives some good results, some good absorption results that makes us boosting our the materials. This also we have filed a patent in the last year. Also we have planned to upgrade this year. This is as a US patent. So this kind of techniques that we adopt, because you know that we cannot making preparing the core cell is not easy task, and we have to adapt. We have to try in different methods. So we tried almost in many cases, like salt gel, hydrothermal, in ultrasonic modes, and in different modes of synthesis we are developed, and we finally got the fine core cell structure that I can show you. That slides maybe. You see the hydrothermal method, but also you can see here here you can see the round cell, round core cell. The zinc oxide is a core, and cerium oxide as a cell. The fine particles of cerium oxide as a cell, and here also with the different size, shape. And previously I showed them. You can find that in that. Spherical powders and Rolex powder also, and not only in the shape, in form, also in the thickness of the core cell also we can modify. We can modify by using the different method and timing. You know, they are all the factors that influencing in the synthesis. So you can find this different thickness range of core and the cell of the rods. But in case of spherical powder, it was a little difficult, but in case of rod, it was easy to form that. Of course, many people, they play with zinc oxide. Zinc oxide is easy to make a different kind of morphology. Like you can see that how much uniform, different sized materials that cerium oxide deposited over the zinc oxide. In the second, the top second, you can easily show the thickness, how it is really attached with core of the zinc oxide cores. So this we applied, we mixed with the cream that we prepared in the pharmaceutical lab, that we also tested, and they gave some good absorption. Like now we have sent this to for the in vivo test to Brazil, because since we don't have the facilities here in Chile. Well, these two are the main just I want to give. Apart from this, we are also working on the environmental sides, like for some photocatalyst work, like in the same kind of cerium oxide, sodium, neodymium, doped cerium oxide for degradation of different dyes, like acid blue and other dyes, like also different material, not only cerium oxide and nickel titanate. Also some works we are working on graphene based materials. So because due to time consumption, I don't want to explain all, but I just want to skip some. But I want to show that some results, more importantly, that we developed like graphene, because the current trend is work on more on graphene and reduced graphene oxide materials. So we also utilize the opportunity to work on many work is going on graphene based material for the photocatalysis and wastewater treatment, especially wastewater treatment filter fabrications. Like and this is reduced graphene oxide with iron oxide as a hybrid composite. Also copper oxide with graphene, because with the different enhanced observation, the Raman spectra that we have obtained good results. Is that this results also with this material also we used for dye effluent treatment. And this also we have recently published in the carbon material journals. And some other works also going on nano cell, solar cell, but transparent electrodes. You can show that the symbol of our department. And anyway, this is just utilize the graphene material that what we are preparing, synthesizing in our material for different application. Since there are many postdocs are working on different fields. So each one have are adapting the different field. So their field that they are working. So it's kind of why I'm mentioning the postdocs are working in different fields. Means maybe I will show in the last slide that is more important. I hope there are many young researchers from in India, especially in Tamilnadu, are watching this conference because to give the information about the postdoctoral opportunities also that I want to mention in my end of the talk. So some graphene oxide filters for removal of heavy metals. This is also a local needs of Chilean government, because here the mining is more a big industry that in Chile. So the heavy metals is more contaminated with the waters. So the removal of heavy metals is more important for many projects, and many researchers are working on the same field. Apart from this,
sorry to interrupt you. You have 1 more minute.
Okay. Apart from this, we also work on max phase and maxine. I think that is a copper. You know, the Chile is big production of copper. Copper in the world. The 40% of the copper production is in Chile. So to develop the copper properties, we also work on copper properties like to make the copper max composite. Not only copper max composite, I think we have. And the next tomorrow we have talk on the professor from Texas University is going to work on maxine. So we also work on the copper maxine composites, because these things are to develop copper material in the nano level maxine, which can give the high mechanical property. At the same time, maintaining the electrical properties of the copper. So these are the works that is going in our group. So some new sintering technique also occurring, and due to time, I'm sorry I cannot explain all. Due to flash sintering technique, which is called a new technique for sintering. From that also we can make sintered nanomaterial within 5 minutes. Within 5 minutes we can sinter the materials at very fast. Even I can say that minutes. You can see that 30 seconds, 20 seconds, and 300 seconds. That then we can sinter the material at high temperature. The new kind of flash sintering, because there are nearly 5 groups only working on all around the world in this kind of sintering. So we are also working on the sintering of flash. So with this, I concluded my talk of the research lines that what we are doing in initial conception in material division. And finally, I just want to give the information about the postdoctoral opportunities that available in Chile. Is recently last 5 years because many people from India is now applying the Fondesit. It's a national funding agency for postdoctoral projects. So I would like to give an information to young researchers. If you have possibility, you can apply this Fondesit postdoctoral to Chile, because I have experienced that I was in nearly 5 years. I worked in the commission of the national funding agency, that I motivated to young students whenever I visit India. The last time I couldn't able to come to VIT, but there are a lot of opportunities. Every year there are nearly 350 to 500 postdoctoral projects are approving. But in the last 3 years, I can say that nearly more than 30 students, Indian researchers, young researchers are coming to Chile. So it's a big opportunity. If young researchers if you have a good publications, good record of publications, and good proposal, they can easily apply. If any doubts, you can. It's my pleasure that I can answer their questions. Thank you so much.
Thank you.
This is just I want to show that it's slide because we are working, we are in the end of the lab, because sometimes the people think that Chile is so far from India, so it is not like that far from India. Nowadays the world is very smaller than you can travel. Here also the developing country, and also many application-oriented projects they are approving, and they are giving more opportunity for young researchers, particularly those who have completed their PhD within 3 years. They are eligible to apply for the postdocs. So I can say that. So it is more for you the opportunity. You can go out anywhere when you have higher education. You can stand with your own legs. Okay, thank you so much for your attention.
Thank you, sir, for the informative and very excellent presentation. A lot of work has been done, it seems. So due to the time constraint, we will scale down to 2 questions, okay. 2 quick questions. So the participants have asked about to comment on degradation of the SOFC.
Okay. Oh yeah, obviously when it's it's you use how long hours we are using, normally generally every cells a minimum at least 1,000 hours it can use. In our case, we have not so far tested the how many hours, because now we are stacking and we are initiating the we are developing the integration of the energy conversion. So only concentrating on the increasing the efficiency. But normally each cell minimum at least 1,000 hours it can work.
Okay.
If even if it use it for continuous.
Okay, sir. So one more last question, sir. SOFC can generate electricity in around 400 to 500 degree. Then how will it be useful to day-to-day practical applications? That's one of the questions from the participants.
But it's like that when we start, it's kind of fun setup that we give the some heat energy. With that we start. But the recent, as I mentioned, the recent trend is to decrease the initiating temperature. But that it's the setup is in the full of with the furnace that we make. That's why it can resist. We are making it in ceramic-based fuel cells.
Okay, sir. So we'll end the session. Thank you for the wonderful presentation, and thank you for accepting our invitation. We thank you, sir.
Thank you for the opportunity. Please, especially I would like to thank Dr. Professor Nirmala, and it is more important you can spread my information to the young researchers who are all interested to come to other part of especially to Chile. And they can apply. If they have any doubt, they can contact me through via mail. Okay, thank you.
Sure, sure, sir.
Thank
Sure,
you.
sir.
Thank you,
Thank you,
Dr.
sir.
Mangal Raja. Thank you very much.
Thank you. Thank you.
Yeah. See you.